We are going to talk some more today about the traveling salesman problem. Traveling. Remember, this is about finding Hamilton circuits in a complete graph with weights on it. You know, something like this. If you have, and you think of these as like 4 places that you want to visit, is often how it comes up in the real world. And the weights are like numbers on the edges here. Right? Those are weights on the edges. And then we want to find a Hamilton circuit with minimal total weight. That is called the traveling salesman problem, finding a Hamilton circuit with minimum total weight. This comes up all the time in the real world when you're trying to find good routes between a bunch of different locations. This can be like trying physically in a car to do this, or like the delivery truck I mentioned several times last time. But also you have to do this in other more abstract settings, like for instance, internet traffic routing has to do things like this, where you have, one computer needs to send something to another computer or to several other computers, and you have to somehow choose a good route among all the different junctions that the internet traffic can go through. So it comes up a lot in the real world. And what we said last time, we just talked about one way to do this is we can do what's called brute force. The brute force algorithm, which is to just list all Hamilton circuits and check them to find the best one, the one with the least total weight. This will always work, and it is at least sort of from step to step easy to do. The problem is this will take way too long in a real life-size graph. In this graph, there's 4 vertices. There's only going to be 6 different Hamilton circuits, which is not so bad to actually check all 6 of them. But if you have a graph with, say, 50 vertices in it, you wouldn't want to do this at all by hand, but even a computer would not be able to do this. So the problem with the brute force is this is computationally infeasible for more than 10 vertices or so. Even a small number like 10 there is really not the kind of thing that you want to be using an ordinary computer to do. And if you have a more realistic number, say for somebody delivering a truck full of packages and they have to decide where to go, it's totally impossible. It would take you billions of years to do this using the brute force. So what else are we going to do? I mean, they do in the real world. People do this all the time. In fact, no more efficient procedure, no more efficient method is known, which always gives the best answer. I'll say which always gives the optimal route. This is a little surprising to me, at least it was the first time I heard about this. The brute force method is far too inefficient, and actually nobody has ever figured out a better way to do it. And also, it's not like this is impossible. Actually, it has not been proved that it's impossible to do it any better way. But nobody has ever figured out a substantially better way to do it. There are a few very simple tricks that you can use to improve the accuracy or to improve the efficiency a little bit, but you can only improve it a little bit. Essentially, there is no more efficient method. No more efficient method is known. If you are thinking about this in the back of your mind and figure out an efficient way to solve the traveling salesman problem, you can become a famous mathematician. This would be a major breakthrough, and it's not only of like pure mathematical interest, but you could, make a lot of money by selling your idea to Amazon or anybody else who wants to do this. This is a big deal, and it is not known how to do this any better. So in the meantime, until we have a better method, actually it is, I think, most mathematicians' opinion that probably there is no better way to do it. Probably it's impossible to have a more efficient way. It's just people tried to prove it's impossible, and that also has not worked out. Anyway, the best we can do, we still have to solve this kind of problem in the real world, though, so you can't just say, like, give up entirely. The best we can do is what are referred to as approximate algorithms. That is, algorithms. Approximate algorithms. That is, there are techniques that will get you pretty good answers, but they will not give you the best answer in all cases. All right? They are not guaranteed to give you the optimal route. So the best we can do is approximate algorithms. These are faster methods, which unfortunately are not guaranteed to give the optimal route. Faster methods which are not guaranteed to give the optimal route, but usually are pretty good. So when the Amazon truck people do this every day, which they do have to do this every day, they are not using the brute force algorithm because that would take billions of years. They are using some kind of other tricks which unfortunately do not guarantee that you get the best answer every time, but they give you something that is good enough and good enough to drive the truck around for another day. That's the idea. These are called approximate algorithms. And I want to talk about two different ways that you can do this. These are ways which are faster than the brute force, but they don't always give you the best answer. You just have to hope that it's going to give you a pretty good answer. So we'll discuss two of them, and today we'll do one, and we'll do another one next time. Neither of them is like the best method because actually nobody knows how to do the best method other than the brute force, which is impossible, impractical to do in the real world. Anyway, the first one is called, they both have cute names, which I prefer to like a person's name. The first one is called the nearest neighbor algorithm. And I'm going to usually just write NN for nearest neighbor. All right? This is a method for looking at a graph and building a Hamilton circuit sort of from scratch, and it's not necessarily going to be the best one, but it's going to be pretty good. That's the idea. And this is actually a fairly simple idea. I think anybody thinking about this would come up with this idea on your own. It's not very fancy. Let's just draw an example here. I have a graph with 4 vertices. I'll call them A, B, C, D like I usually do. And let's say the weights on this one go like this. A 1 here, a 1 here, a 2 here, a 4, a 5, and a 3, like that. Let's say those are the weights for my graph. For the nearest neighbor algorithm, first of all, you just pick a starting point. So when I ask you to do the nearest neighbor algorithm, I'm usually just going to say, like, do it starting at A or something. Pick a starting vertex. Then you're going to choose edges one at a time. And as you go, you choose edges one at a time and pick the cheapest edge. Each time as you go. All right, and you just every time you have a choice to make about which edge you're going to use, you just use the one wherever you're at, which has the lowest weight on it. You pick the cheapest edge each time as you go, and I'll just say, don't finish early. You're not allowed to go back to a vertex you've already used, and you're not allowed to go back to the beginning until you've visited every vertex. So I'm going to write, actually, can I just say, don't reuse any vertices. Of course, that's never allowed in a Hamilton circuit, right? So in this case, here, let's say for this graph here, starting at A, I'm going to redraw like just the vertices, and I'm going to indicate which edges we choose every time. So starting at A here, I said you just pick, I have three choices, right, for this edge. It could be, you know, this one, or this one. And I'm going to choose the one which is the cheapest in terms of the weights. That would be the one on top, which is a 1, right? So my first choice is this edge, which is a 1. Come on now. Right? That's my first edge that I pick, because that was among the three choices that I had, that was the one with the lowest weight. So I go this way, and now I look from B. From here, what are my choices? I have two other edges to choose from. It's the 1 or the 2. Which one do I pick? I pick the 1, because I'm using the lowest weight edge every time. So I go down this way now, and that was also a 1, right? This is called the nearest neighbor, because if you think of those weights as if they were like distances from one to the other, it's just every time you have a choice to make, you choose the nearest one, or the lowest cost one, or whatever. All right, now from C, really I only have 2 choices remaining, but actually I can't go back to A because I've already used A. Like, I don't want to go back there until I'm done with the whole circuit. I don't want a sub-circuit, I guess. So anyway, I have to go to D at this point, which was a 3, and then from D I have to go back to A to finish, and that was a 4. All right. So my circuit that I have constructed is apparently A, B, C, D, A. All right. This is the nearest neighbor procedure. You just choose the edge which has the lowest weight every time. For each time you have to choose. All right. And then what is the weight? The total weight of this one is 1 plus 1 plus 3 plus 4, which is 9 in this case. And actually, I did the brute force. It turns out 9 actually is the best route that you can make in this example. So in this case, I'll say here A, B, C, D, A is actually the best Hamilton circuit. All right, but we did it without checking like all possibilities. This is called the nearest neighbor algorithm. Any questions about that one? We're going to do some more examples. But yeah.
I just have a question about the arrows. Does it matter like where they go on the lines, or is it like?
Oh no, I just sort of put a bunch of arrows. You mean why did I put 3? I suppose I put 3 on all of them, but no, it doesn't matter.
Okay.
Yeah, I was just being here. I put a lot more hours on that one. It doesn't matter. Thank you for the question. Yes, I just want to point out, this is much faster than doing the brute force. If you think about sort of how many steps are required in order to do this, you start somewhere. You basically, in this case, I basically had 4 decisions to make. I chose the first edge, then I chose the next edge, then the next edge, then the next edge. So for, can I just say with, say, n vertices, the nearest neighbor procedure requires how many choices? It's basically n choices, right? Here I had 4 vertices, and I had to choose 4 different edges, one after another. And that's how long it takes. How long will it take you to do this procedure? Well, it's just however many vertices there are. You have to make that many individual edge choices. All right. Compare this to how many steps would the brute force take? In this case, you'd have to check 6 different possibilities. So with n vertices, the nearest neighbor procedure requires n choices. The brute force requires, this is what we talked about this last time, n minus 1 factorial checks. And when the n is big, this is super, super big, right? This is super duper big. When the n is large, this number is just going to be n, but this is going to be n factorial, which is far greater. So the nearest neighbor is much, much faster. That's because this number here is super big, right? You don't want to do that many steps unless the n is like 3 or 4, you could handle it on paper, but more than that you would never want to do on paper. Whereas the nearest neighbor thing is easy to do, on our next homework or test or whatever. It's totally reasonable if I ask you to do the nearest neighbor on a graph with, say, 8 or 9 or 10 vertices. It's not a problem. But the brute force would be totally impossible in that case. All right, let's just look at a couple more examples. How about this? I just got 2 others to demonstrate. As usual, I'm going to call them A, B, C, D. And the weights this time, I'm going to say 1, 2, 4, 5, 3, and 10. I've realized over the past few weeks that some people don't like copying down my pictures. I know it's frustrating if you copy down slightly wrong, then everything will be wrong. Sorry. I have some bigger examples we're going to do later on. I actually printed them out. A little something to look forward to. A little handout. Anyway, let's do it again. So let's try the nearest neighbor starting at A. Once you get good at this, you could often just like do this entirely in your head, but just to try and draw it out, I'm going to just draw the vertices, and then starting at A here, which anyone want to say which edge should I take? Should I go to B, C, or D first? B, I think he said. B, C, and D all kind of sound the same. But yeah, you should go over to B first. That's a weight 2. Remember, the idea is just as you go, you always choose the lowest cost edge. All right, from B, I have 2 choices now. I could go diagonally or straight down. That's a 5 diagonal or a 1 straight down. So I'm going to pick the 1. I'll go down here. That's a 1. Now, actually, I'm sort of done with my choices. You can't go back to A because that makes a subcircuit. So I have to go across the bottom, which is a 3. Then I have to go back up the left side, which is a 10. So here the weight. So I guess the circuit I made was A, B, D, C, A, right? And the weight, if I add this up, is 2 and 1 and 3 and 10. That's 16, I believe. All right. Okay, that's the nearest neighbor procedure. There's not a lot to it. I hope you feel like this is pretty straightforward. Let me just point out, actually, in this example, this is not the best Hamilton circuit that you can do. Actually, in this example, in this one, the nearest neighbor doesn't give the best answer. Anyone just looking at the graph, can you tell me a better circuit starting at A? Yeah. A, B, C, D, A. Yeah, if you go, really, when you look at this graph, you'll see that 10. You really want to avoid that 10, don't you? So it would be better if you go across A, B, and then the diagonal here, A, B, C, D, A. That would avoid the 10, which is quite good in this case. This one, the weight would be 2 plus 5 plus 3 plus 4. That's 14, which is better. All right, so the moral of the story, the nearest neighbor does not always choose the best answer. It's true. But, you got to just sort of hope that it's going to give you a pretty good answer. Actually, sometimes, if you get very unlucky, sometimes the nearest neighbor actually picks a very bad answer. Making those cheapest decision every time sometimes kind of backs you into a corner. It's like real life, isn't it? If you go through your whole life just doing the easiest thing at every step, that works out for a while. Maybe most of the time that works out, but sometimes actually you end up in a very bad situation. So it could be something like this, for example. If the weights are like this, 1, 2, 3, 1, 1, and 100,000. If you do the nearest neighbor starting at A, this is an example in which if you choose the cheapest edge every time, you end up in a bad situation. All right, so here, the nearest neighbor here is very bad. You end up having to, you tick the 1 every time, but then you end up stuck on this 100,000, which is definitely you don't want. So the nearest neighbor actually, from a theoretical point of view, is not always going to do the best thing, and sometimes it will end up doing the worst thing. Although if the numbers on your graph are all sort of in the same ballpark, if the numbers are all similar to each other, or if they're like statistically random numbers, which these are definitely not because that one is way out of whack with the others. If they're more or less random, then the nearest neighbor actually works quite well. There are some situations in which the nearest neighbor ends up giving you a very bad answer. But in real life, those tend not to come up very often. All right, I got one that's a little bigger, and I put it on a handout just so you don't have to copy down my picture. You folks sitting in front may be able to do this faster than I can get to the paper to the rest of them. But I want you to try to do the nearest neighbor algorithm on this one. This is just 5 vertices. So let's do the nearest neighbor here, and I guess let's just start at A. Oops. Everybody got one? I think. So let's do nearest neighbor. If you know what you're doing, this will only take you a moment to do. Hardly worth the handout, was it? It would have taken you longer to copy down the picture than to actually get the answer. I'll give you a moment. Tour just walked by while I was not saying anything. Does that reflect badly? I don't know. Start at A and choose the cheapest edge every time. Can we talk about it? Starting up here, you start at A, you have 4 choices, right? The 7, the 1, the 3, or the 5. I better pick the 1 because you want to do the cheapest edge every time. So I'm going to start by going down here. That was a 1. Going down to D, right? Unfortunately, if you mess it up early, then your whole situation is screwed. You will be wrong permanently. From the D, where did you go next? Yeah, next should go to B. Since I'm at D now, my choices are the 4, the 2, or the 5, and I'm going to pick the 2. So I go over here. That was a 2. Next, I'm at B. My choices are the 5. Actually, I can't go back to A yet because I'm not done yet. I could go straight across, which is a 3, or down, which is a 1. I'm going to pick the 1. So I go down like that. That was a 1. And then now I only have one more place to go. You have to go over here. to avoid finishing early, and then I go back to the beginning. This edge was a 6, this edge was a 7, all right? This also is a scenario where you might feel like maybe my initial choices set me up to do badly at the end because I ended up having to pick the 6 and the 7, which are the worst edges on the whole graph. But anyway, this one, my answer, just to write it out, is A, D, B, C, E, A, right? And the total weight, if you care, you can add those numbers up. The weight was 1 and 2 and 1 and 6 and 7. That's 17, I think. Yeah. All right, that's how we do it. This is the nearest neighbor algorithm. Sometimes gives you good answers, sometimes gives you bad answers, but in general, I said, like in the real world, you generally would expect us to give you pretty good answers. Something a little strange about the nearest neighbor procedure. Something strange about this is that it matters sometimes where you start. Like if you do the procedure starting at A, you get something. But sometimes if you start at a different vertex, actually you get a completely different answer. So I wanted to demonstrate that. Let's just do it with 4 vertices again. And let's put a 1, a 1, a 2, 4, 3, and 5. So this is A, B, C, D, all right? And I want to see what happens if we do this but start at different points. So if I start at A, what I get is from A, I should go across the top first, and then down the diagonal, which is another 1. These are 1s. And then across the bottom, which is a 3. And then across the diagonal again, which is a 4. And this weight is 1 plus 1 plus 3 plus 4 is 9, right? So this is the circuit that you get by starting at A. It's that sort of hourglass shape, right? What if we start at B, though? That was starting at A. What about starting at B? Well, then, what does it look like? Now, I didn't mention this actually. What if there's a tie? This is, unfortunately, sometimes there's a tie. And starting at B, you have 2 choices here that are both 1s. And if it's a tie, the nearest neighbor procedure, you just have to pick at random one of the things which is tied. So I'm gonna. How about we choose the horizontal edge in that case? It turns out in this particular example, it doesn't matter which one you choose. But I'm gonna choose this one first. I guess I didn't put directions before. It's not really important. I'll choose the first one going across. And then from A, I can go down with a 5 or diagonally down with a 4. I will take the 4. And then from D, I have to go across the bottom, which is a 3. And then I have to go back to B, which is a 1. So this one actually is 9 again if you add it up. And in fact, those are the same answer, really. I mean, they represent the same circuit, just starting and ending at a different point, right? And the direction is different. Like this one goes around that way, this one goes around kind of the reverse way, but it doesn't matter. These two really are, I will say these are basically the same answer. They represent the same Hamilton circuit, only just starting at a different point, but you're doing the same circuit. And they're going in different directions, but really it's the same either way, starting at A or starting at B. But check it out. I'm just going to write down, because I never wrote this before. If there's a tie when we're trying to make a choice, I will just say pick either way. And in this particular example, if I had ended up choosing the diagonal at that first, you'd end up getting the same answer. Although it's not always the case. Sometimes your random choice actually does make a difference. But anyway, that's starting at A and starting at B give you more or less the same answer. But I was trying to explain that starting at different points can give you a different answer. What about starting at C? That's this one down here. If I start at C, or where should I go first? Somebody can shout it out. Up to B, right? That's a 1, the diagonal edge going up. So I go up here, which is a 1. Then from there, I follow the other one. Yeah. Then from there, I follow the 4. And then I go back there with the 3. So this is again the same. I'm getting worried here. I'm trying to demonstrate that you don't always get the same answer. The last one is not going to be the same. But anyway, this is again the same old circuit, that same like hourglass shape. Check it out though. If we start at D, what happens? Then starting at D, I have, my choices are the 2, the 4, or the 3. So I'm going to use the 2. And now you can tell it's going to be different. It's because none of those other answers actually used that edge on the right side. Starting at D, you pick the 2 first. Then I have 2 choices. I could go diagonal down or straight across. And that's, I'm just going to have to choose at random. Let's say I'll go diagonally. That's a 1. And then from there, I have to go up here, which is a 4, and then back to the beginning, which is that's a 5 over there. And then this is a 4. All right? So this is what happens if you start at D. You get something different, right? This is weight 5 plus 4 plus 1 plus 2, which is 12. All right? So in this case, starting at D actually gives you a worse answer than starting at the other 3 points. That's what I was trying to demonstrate. All right. So the fact that the nearest neighbor is comparatively very easy to do, if I ask you to do it, any one of these is really easy to do. Actually, we can do pretty well if we do what is called the repeated nearest neighbor. That is, if you really want to make sure you're getting the best one, now you may not get actually the best one, but to maximize your chances, you should do it over and over again, choosing every different starting point and seeing which one gives you the best results. This is, it makes it slightly more complicated to do or slightly longer to do, but it's nothing like the brute force method. The brute force is still far, far more than this. So the repeated nearest neighbor procedure, how you do it is you just check the results of the nearest neighbor starting at any of the vertices and choose the best answer. All right, this is called the repeated nearest neighbor. And if you really want to get good results when you're doing this, you might as well do this way, the repeated nearest neighbor. That is, you actually go through it over and over again, starting at all the different starting points, and see which one gives you the best results. This is still far easier than the brute force method. And this is still, very much workable in the real world. All right. So let me just say, in that example that we just talked about, I lost my picture. In this example here, you could say, oops, come on now. All right. We already pretty much did all the work, but I just want to summarize how this would look if this was like a homework problem or something. For this one, use the repeated nearest neighbor algorithm to find a good Hamilton circuit starting, let's say starting and ending at B, all right? This can be slightly confusing because I said use the repeated procedure, which means you're going to go through and do this for every possible starting point. But then I want you to write your final answer as a circuit which starts and ends at B. So we check all possible starting points and choose the best circuit. And in this example, we already did the work. In this example, the best circuit is this one, right? We get this one, which is, how do I write my answer? I said I wanted you to write the answer as a Hamilton circuit which starts and ends at B. And so how I write the answer, remember they're labeled like this, A, B, C, D. This is B, C, D, A, B, if you go around that way. Or you could go around the other way. B, A, D, C, B. All right? So you have to go through this problem and find the best circuit using each different possible starting point. And then you pick the best one out of all those, and you write the answer as if it were a circuit starting and ending at B. All right? That's what I wanted you to do here. I don't know if that seems confusing. I find it's sometimes a little confusing. All right, I got one for you to try. I thought actually let's just do the one on the handout, right? You can turn it over if you already filled up all your space or something. But I would like to find a good Hamilton circuit on there using the repeated nearest neighbor algorithm. Add. So let's see if we can do this. Use the repeated nearest neighbor to find a good Hamilton circuit. All right, find a good Hamilton circuit starting and ending at C. What you should do is check all the different starting points. The fact that I said starting and ending at C doesn't matter until you come to actually write your final answer. When you write your final answer, just write it as if it was starting at C. I'll give you a few moments and then we'll talk about it. This handout has the same graph on both sides, so if you want to turn it over, go for it. should be working out. What happens if I start at A? What happens if I start at B? What happens if I start at C? And so on. Well, it means, yeah, you do it. You do it again and again.
Okay.
Starting at each day. So this is what you get when you start at C. Okay. Should also think about what if I start at A. Okay. Let's take a couple more minutes and then we'll chat about it. How's it coming over here?
I don't know. I don't know if I did this again or if I was like supposed to do like a. I started at C, but is it not just like going?
You should, yeah, although you shouldn't really start at C. But that's part of it. Just one of these choices. You started at C.
Yeah.
Here, here. Yeah, from here you shouldn't go back to C because you missed. Like from here you have to go back to C.
Let's talk about these. I see varying degrees of success here. You have to, it'll take a few minutes to work through all of this, but you work it out, first of all, starting at A. This is the example that we already did last time we looked at this, thing on the paper. What about if I start at B? You got to work that out also. If you start at B, you take the 1 first, so it goes down here, and then from there, my choices are the 5, the 6, the 3. I should do the 3. So it goes up here next. From there, I'm going to choose the 1 to go down there. And then I have to choose this 4 and this 3. So this one is what you get when you start at B. I hope that you got something like that, starting at B. And the weights here would be 1, 3, 1, 4, and 3. So this one adds up to 12. Right? So starting at B, you get a circuit with a weight of 12. Okay, what about, you got to just do this for each different one. How about starting at C? No. I didn't want that. I want this. No. Yes. It'll be worth it. Okay, starting at C. Again, I find it easiest if I just redraw the vertices. Starting at C, which is this one, I'm going to have to choose the 1 first, and then the 2 here, and then the 1 here, and then I have to pick the 7 and the 6 to get back. This actually is the same as the first one there. This is a 17 again, right? This choice starting at C, I end up with the same as if I started at A. What about starting at D? Again, I put my vertices, my verts. From D, my choices are a 4, a 1, or a 2, or a 5. I take the 1, then I'll take the 3, then the 1, the 3, and the 4. This is what you get starting at D, which is the same as that one starting at B. This is 12. And then finally, I'll squeeze it in over here. Starting at E, what is it? It's going to be that same 12 again, it sounds like. I go the 3 first here, then the 1. Yeah, you're going to end up getting this same one again. This is the 12. All right? All the work is done at this point. You just have to come up with the answer. So, having done all of these, this is kind of a pain to do. This is the repeated nearest neighbor procedure. I've got 5 different little answers. I choose the best one overall, and many of them, you will expect, many of them will end up being the same. But I choose the 12, right? So, the best answer is the 12. And writing this, remember the question said, find the best one starting and ending at C. So I write this circuit starting and ending at C. So I'm looking at this picture here. Remember the labels went A, B, C, D, E. So write this circuit right here as if it started and ended at C. You know, any of these you could write if you wanted to as if they started and ended at C. So I'm going to write this one starting and ending at C. And it could go either way around. I'll go C up to A first, and then it's D, E, B, C. All right, that's that circuit written as if it starts at C. Or you could go the other way around. Then it would look like C, B, E, D, A, C. All right? That's how we do the repeated nearest neighbor algorithm. Anybody got questions about that? I hope that worked out for you. And I think that'll do. You know, we got 2 minutes left, but this is all I want to say about the nearest neighbor. Next time we will talk about another procedure for doing this same problem. See you all then. We will have our quiz also based on the homework for today.